Second derivative test, yeah. Okay, so let's set up our table, and I don't know if we'll spend a ton of time going through, maybe on one of these we'll go through the tests, but what I really want to focus on today is kind of the algebra associated with setting up the calculus. Okay, you might remember that back in last chapter, we just focused on being able to execute the derivative steps, right? Follow the rules. And I said, we're not going to worry about simplifying too much, but now we have to, right? Because now we're trying to find critical numbers, and so we have to set our derivatives up so we can find the critical numbers easily, right? Which means we can set them equal to 0 and solve, or we can find out where they're undefined, okay? Now, if I were to expand this whole thing out, which would we don't need to, but if we did, what kind of function would we get if we expanded this out and simplified? Okay, so we get a 7th order polynomial, right? It'd be a big, ugly, but the key word there is polynomial, right? It would be a polynomial. And so right away, and I think this is not a bad idea to do. I mean, I know you're anxious a lot of times to get going on the problems and get into the work and get things done, but before you jump into stuff, I really think it's crucial that you just take a second and think, even right now, just a little bit about what this problem is going to look like. Right? We're going to have this polynomial. If I differentiate polynomials, what do I get back always? Smaller polynomials. So right away, can you tell me, before we even launch into doing any derivatives, is there any place where this function or its derivatives are ever going to be undefined? No, nowhere, right? So the only thing we're going to be looking for, the only kinds of critical numbers we'll ever need to search for will be the zeros of the derivatives, right? Okay, so let's spring into action here and do some stuff. The domain is, there's no place that's restricted, right? All real numbers are okay. So we need to take some derivatives. Let's take the first derivative. Okay, what's the rule going to be that we have to follow first? Okay, we've got to use product rule. So we've got first times derivative of the second. So we get x cubed times. Now, what's the derivative of the second going to look like?
4 is going to be x plus 2.
X plus 2 cubed, right?
Yep.
Times 1, good. Okay, plus the second. I'm going to go back just a little bit here. Plus second times derivative of the first, and what's the derivative of the first? 3 x squared. Okay, why did I color code it the way I did? Okay, because we want to try to make this thing simplified. We're going to be setting it equal to 0 and solving, and so we want it factored, right? Last chapter that wasn't an issue, but this chapter it is. If we want to factor this, we want to be looking for like bases, right? Because we can factor out a power of a like base. Agreed? Okay, now look at let's focus on the powers here. I've got my base x cubed and my base x squared. Come up with a rule for me, please. What if I have like bases, what power of that like base can I undistribute or factor out of each term? Okay, the least of the two powers, right? We'd say it's the least common power. Does that make sense? Okay, because this one only has an x squared to give. This one could give up to an x cubed, but this one can only give an x squared, right? So we're going to pull out from both terms, we're going to pull out an x squared, right? And now the other like base is an x plus 2. So we can take out an x plus 2 cubed. Good. Okay, and what are we left with then? in the brackets, what are we left with? So we're gonna start off with what's all the first term stuff that's left over. We can do a little bit of cancellation, can't we? Right? When we factor out an x squared, that factor goes away completely from the second term, and we're only left behind with a power of 1 from the first, right? Okay, what about the other base? We factored out an x plus 2 cubed, so it's gone completely from the first term, and we're left with only one of them left in the second term, right? Okay, is that an accident that it happened that way?
No.
It's got to be that way, doesn't it? Wouldn't you agree? And there's kind of some subtle relationships going on here, but this should all come together now. The power difference between each of these bases in the two terms, because it's the product rule, is always going to be 1, isn't it? Right? Because this base, in one of these two terms, we've had to subtract 1 from the exponent, right?
Right.
So they're always just going to be 1 different. Make sense?
Yeah.
The one that's smaller is always going to be, one of them is going to be smaller in one term and the other one's going to be smaller in the other term, right? So you'll always get this kind of behavior where one of the two factors will cancel completely from one term and the other factor will cancel completely from the other term, right? And you're left behind with only one of each. That makes things very convenient because then it gives us something inside the brackets that's pretty easy to simplify, right? From the first part, we're going to get what left over then?
4x.
4x, good.
Well, can you times that by 3? Oh, no. Never mind.
Okay, make sense? Okay, plus
X, 3x plus
what's left from the other term?
3x
3. X plus 2. And that's simple, right? That's easy stuff to put together in there, isn't it? Right? So if we distribute the 3 and combine like terms, then we end up with the result, x squared times x plus 2 cubed times, what do we get, 7x plus 6? Okay, make sense?
Yes. So you just set each one of those equal to 0?
Right, and we said each of those equal to 0, exactly.
So
Are you gonna do second derivative?
Okay, so then we'd have to do a second derivative, wouldn't we?
Yep.
Right? Okay, so what about this? Now, is there anything in here that maybe we could do? Let's talk about the second derivative. Would you agree this is going to be pretty easy to solve when I set this thing equal to 0?
yeah.
Because I've already got it factored, right? So I can just set each of these individual factors equal to 0 and solve to find the first derivative critical numbers, okay?
Like 0, -2,
Well, right, 0, -2, and -6/7, right, would be our 3 first derivative critical numbers that we could add to our table, right?
Yeah.
If I set each factor, the blue, equal to 0, because now we apply the zero product property. A product of factors equals 0 only when individual factors are 0, right? Okay, so how about taking the second derivative? What do you suggest here for approach for taking the second derivative?
Like the first.
Okay, we could differentiate the first row of the second one if we want to. We could go ahead and just differentiate this because we have a generalized, and let's take just a second to remind ourselves how that works. We have a generalized product rule for a product of 3 factors, right? If we want to differentiate u times v, let's do w. I have to think my alphabet there for a second. How does that work? Okay, good. So we're going to get as many terms in our product rule as there are factors. And just remember that in each of those 3 factors, one of the factors is prime, right? So it would just look like, it's going to look like u, in any order you want to, uv w prime plus u v prime w plus u prime, oops, I do that right?
Yeah.
you
U prime V W, right? So we can do it that way, that's fine, it's not that bad, right? And then we're just gonna have common factors to pull out from each one. That's fine to do. Do you see a way we could maybe avoid that though? Is there an easy, could we cheat a little bit? I mean, because we've got a blue and an orange and a black, and we could easily just differentiate using the extended product rule. Does anybody see? And that's fine, that's fine.
Could you like get rid of the x's? Like an x from each one?
I can't do that because the x plus 2 is tied up inside this power.
But could you distribute the power?
Okay, but I could distribute the x squared. I could easily, because it's a single term, I could easily distribute that through here, couldn't I? You see what I mean? I could distribute the blue over the black, right? Do you see maybe a little advantage of that?
Yeah.
Okay, so if we do that, it's not essential, but it's just a little trick that, it makes things.
You're not missing any more steps, like you're not shortening the steps, number of steps.
Well, you are a little bit, just because you're not having to write out,
I'm shortening the product.
you're shortening the product rule just a little bit.
You
And
know, like if you just go straight from the product rule like that, you wouldn't have to do the whole square times the 7x plus 6.
But there's less numbers.
right, I see your point. Either way, it's not gonna be much different, but the calculus steps are gonna be a little bit simpler. And the only reason that would make sense to do is because it's gonna be so easy to factor out those x squareds again. So this is kind of I'm gonna put the good old optional star by it. So this is just an optional step. You don't have to do. Well, that's a terrible star. Fix that. That's a little better star. So we could rewrite this if we wanted to as x plus 2 cubed times 7x cubed plus 6x squared, right?
Yeah.
See what I'm saying? And so now when we apply the product rule to get our second derivative, arguably this is just a little bit easier because I only have to use the regular old two-factor product rule. So what do we get then? Times 21x squared plus 12x, okay, plus this whole thing, right? 7x cubed plus 6x squared times x plus 2 squared. Okay, so then what have I got? I've got, what kinds of bases do I have here? Well, I could factor out, from each of these, I could factor out x's, couldn't I? See what I'm saying? Like on this side, I could really take out now, I could pull out a 3x, right, from this stuff. So I'd end up with x plus 2 cubed times 3x times what would be left over? 7x plus 4, right? Plus, I could pull out an x squared over here, right? X squared times 7x plus 6, okay? And then, I guess I could put that 3 with the x squared. And then I've got an x plus 2 squared. Okay, now we can easily factor this, right? What's name a like base? X plus 2. So how many x plus 2's can we factor out? Squared. Okay, so we get x plus 2 squared, and that's going to do this, right? What's another like base? We could take out a 3x. Good. Okay. Leaving us with, so that's gone, the 3's gone, I'm left with an x on that side. And that's all we can take out, isn't it? Right, then what are we left with? Okay, so from over here we get what? We get an x plus, okay, I get an x times an x plus 2 times a 7x plus 4.
Wait, where's the X?
Wait, the X.
Did I mess that up?
X2 is on the right.
Oh, no, sorry.
So it shouldn't be multiplied.
Sorry, yeah, that's gone, the X is gone completely, isn't it? Whoops.
Yeah.
Yep, you're right. Okay, so this guy is not there. Plus, now how about from over here?
7x plus 6.
So we got an X times 7x plus 6. Right?
Wow.
Okay. And so, I mean, it was, there's some calculus to do there, but it's not horrible, right? Now, this is all pretty easy to combine, isn't it?
Oh, yeah.
Right? So if we went that last step here and simplified this even further, we've got a factor 3x times x plus 2 squared times, what are we going to get? If we distribute this, I'm going to get, this whole thing is going to become, what, 7x squared plus 4x plus 14x, so plus 18x plus 8. And this whole thing is just going to become 7x squared plus 6x, right? So then we get
14x squared.
plus 24x
Yeah, plus 8, right?
plus 8. And I guess we could take an additional 2 out of that if we wanted to.
Wait. What happened to the one?
I'm just adding those up.
Okay.
And so now we've got these in positions where we can set them equal to 0 for both derivatives. Oops, not there, sorry. Actually, right here is where we want to set it equal to 0, right? And we already did that, found our 3 first derivative critical numbers. Here we could find, what are our second derivative critical numbers? 0, negative 2, and
We get 2 from that?
yeah, potentially, right? We'd have to solve this quadratic, like using the quadratic formula or something like that,
So the
right?
negative 2 from above doesn't work that means, right?
Okay, so then the negative 2 from above
And the 0.
is, and 0 are gonna be double critical numbers. They're critical numbers of the first and the second derivative, right?
Wait, why are we trying to come up with the
Because critical numbers in the second derivative are the places where potentially the concavity can change. So they're potential inflection points, right?
Okay.
Okay? Now, I'm not even gonna mess, this is a much harder function to deal with than what you got on the assignments. Only reason I brought this one up is just because I wanted to illustrate, kind of algebraically, some things to be aware of, right? Like the factoring issues, right? Okay, we want to make sure that when we're not following our impulse to like distribute everything and expand it out. We don't want to do that. We want to keep things as factored as we can, right? Mm-hmm.
For the polynomial that we have at the very bottom,
Mhm.
it had another negative 2.
Did I miss something?
No, it's just when I did the factoring to see what the 2 critical numbers were at 0, it was negative 2 fifths and negative 2 fifths.
Okay, so this did factor then.
Yeah.
Yeah, this does, evidently this does yield some zeros. And all we'd have to do to find them though, right, to find the critical numbers, we already know that this one's gonna give us, we're gonna get x equals 0, x equals negative 2, and then whatever, if we take a 2 out of this, we're left with 2 times 7x squared plus 12x plus 4. So we're just going to set that equal to 0 and solve that quadratic equation. And if we get, we're either going to get 2 real roots or no real roots, right? And if we get real solutions to this quadratic equation, and we can check real quick, b squared minus 4ac, 144 minus 4 times 28. So we are going to get 2 real roots out of that. But I'm not going to mess with it now. We could though, right? We could find out what those are and add those to our table, okay? But like I say, I don't want to get bogged down dealing with this really cumbersome big problem. It's not, you don't have any that are quite this big. Okay? They wouldn't have, I changed this one to make, what made this a little harder is I made the powers of the 2 factors bigger. That made it harder to deal with. But I just wanted the additional practice factoring, okay? Okay, so our work is done there. A couple other things I wanna, just before we move on, I wanna address though. One of them is this. How about, let's pick a really easy function that'll illustrate this. So like, let's pick, I'm gonna do two of them. Let's do one of them that's f of x equals x to the fourth. So we get super simple derivatives, but something's gonna happen here that's you haven't maybe had to deal with before. What's our first derivative gonna be?
4x to the third.
What's our second derivative gonna be? 12x squared. Okay, so our critical numbers are just 0, right? The only critical number we get, but would everybody agree that it's a critical number of both derivatives?
Yeah.
Okay, so when we make our table, oops, so we get this, we get 0 is a 0 of both derivatives. Okay, so what's that mean? That means the second derivative test failed here, right? Because the second derivative test is the one where if we have a 0 of the first derivative, the sign of the second derivative tells us the concavity, right? And that tells us if it's a minimum or a maximum. Okay, but the second derivative here was 0, right? So what do? We have some options. Well, for sure, what's one thing we're gonna need to do? Not give up.
Wait, is this a new question?
Yeah, new problem.
Okay, we were still figuring out last one, okay.
What are we doing?
So the last one, we were done with it. All I wanted to do on the last one was just tackle the idea of finding the zeros of the derivatives. Okay. Now we're moving on to a much easier one, but this is different. Look what happened here. We haven't seen this before, right? Where we've got a simultaneous 0 in both f prime and f double prime rows of the table. So it's a simultaneous critical number of both derivatives. So what do you think we need to do? The second derivative test failed. No. Test points. Yeah, we just need some test points, don't we? So let's try test points. How about -1 and +1? Okay, now we really have our option here, but I always told you that you're better off working further down the table, right? So let's go ahead and check the signs of the second derivative. Okay, so the second derivative right here, what can you tell me about the sign of the second derivative? It's always non-negative, isn't it, right? So we're gonna get positive there and positive there. So what does that tell you then? Is this an inflection point?
No.
It's not an inflection point because it's not a point of transition. It doesn't change concavities, right? It's going from being a positive concavity to a positive concavity, so it has to be a minimum, doesn't it? Right? The only way that we could join a positive concavity and a positive concavity is going to be if we do something like this, right? Because would you agree?
Yeah.
Okay. So then this is a minimum, and are there any inflection points?
No.
No.
Wait.
Okay,
Sorry.
that's all right.
I thought this was when there was an S.
Okay, that's where there's possibly an S. An S, though, is only going to occur if we're changing concavities, right? So if we change, for example, if our second derivative row, say we had a 0 here and we went from positive to negative, then that would have been from concave up to concave down.
No, I meant where it went positive. Remember that one time you originally kept going positive, but we flattened out.
Yeah, so that's what it
Is
is.
that what it is?
That's what it is. So this is one where it's positive and then positive again. Let's go ahead and just verify that by checking the signs of the first derivative. If we check the signs of the first derivative, when x is negative, what's going to be the sign of the first derivative? Negative. And when x is positive, it's positive. So doesn't that make sense? We're going from the first derivative test would have told us we're going from a decreasing function to an increasing function through a horizontal tangent, right? Okay, now what's nice about this is the two things, we've got inflection points versus relative extrema are mutually exclusive. It can't be both. It's one or the other, right? And so really we could have used either one of these rows, And once we know that it's a minimum, we know that it's not an inflection point. Right? Because they can't be the same, they can't coexist. Okay?
Wait, what if it was like, the cubic function that doesn't have a minimum?
Okay, that's interesting you say that. That's the next one we're gonna look at. So what if we, so this is an example where we got a relative minimum when we got these going on.
Yeah.
Now let's look at an equally simple function. Let's just take f of x equals x cubed. So what's our first derivative? 3x squared. Second derivative. Okay, so we get the same kind of a thing going on here. We got a 0 of the first derivative and the second derivative at x equals 0. Okay, this time if we go down to our second derivative, what do we find? When x is negative, what's the sign of the second derivative? Negative. Okay, when x is positive, oops, this will be a positive one.
Positive.
It's positive. And so that is an inflection point, right? What's that one going to look like? Clancy, what's that one going to look like if I'm going from negative concavity, so bowl down, to positive concavity, bowl shaped up, through a horizontal tangent? So there's my horizontal tangent. Doesn't that mean this one's got to go?
That's the one I was.
That's the one you're talking about, right? Okay, make sense? So so we know it's an inflection point because it's changing concavities. So is it a relative extrema?
No.
Can't be. It's not. We don't have to do this, but just to verify it, not that you'd even want to do this because it's a waste of time, but just to show you that that has to be the case. What's the sign of the first derivative always? Positive. So is this a transition? No, it can't be an extremum then, right? Because it didn't change signs. And that coincides with our picture. Think about the ant. He's walking uphill, and he's walking uphill the whole time.
Mr. Oya?
Yep.
Really quick, why don't we put a 0 with the F?
Oh, we could. We just didn't. Yeah, it is there. You're right. It is the point 0, 0.
I was
We just didn't bother. But no, you're right. In both cases, it would be the point 0, 0.
So you can tell though, if it's going to be an S or if it's going to be like at that point like a parabola type shape if it's an exponent. Like if it's
You're right. I mean, you're right. And as you get better and better at this, what you're going to see is, you'll be able to just kind of look at this thing and say, well, the original function is an odd function. And we haven't really talked about symmetry yet, but if it's an odd function, it means it has rotational symmetry about the origin. And I'm not going to do that today, but we'll do it in the next week. I'll spend a day just reviewing symmetry stuff, or part of a day. So that would be one where we could spin it 180 degrees and it lines up, which is what this one does, right? If we had a function like this that's even symmetry, that's got to be reflective symmetry around the y-axis, which this guy has, right? So you're right. I mean, there's a bunch of different ways you could have probably seen what was going to happen there. But sometimes it might be harder to do that because the other functions won't necessarily have those kinds of nice symmetries. It might be a function that instead does something weird like this, where maybe it goes something like that, right? Where it doesn't have that symmetry. See what I'm saying? But you still get something here that maybe was a simultaneous 0 of both derivatives. So to kind of summarize what our strategy is, you tell me, if we get zeros for a certain critical number, if we get zeros in both the f prime and the f double prime rows, what do we do?
Test points.
Yeah, we're just going to pick some test points and we're going to check really either one. Doesn't really matter. I mean, either one of these would have been conclusive, but as a general rule, it's better to work further down the table. Okay?
So the second derivative just shows us inflection.
Well, the second derivative shows us concavity. And inflection points are changes in concavity, right? Positive second derivative corresponds to what for a function? Well, concave up. But it's a positive, meaning an upward concavity, right? And remember, positive concavity means a happy function, so it's bowl shaped up, right? Negative second derivative corresponds to what feature on the graph?
Yeah.
downward concavity, sad face, right? Okay. I mean, yeah, you'll have to probably keep thinking about it a little bit, but I just wanted you to see a couple examples of that. Okay, real quick then, the other thing that I thought was maybe worth looking into was one like, let's see, there's one in particular I wanted to do. Something like that would be good. Yeah, let's do that one. Okay, I'm gonna make it a little harder though. So this, once again, this is a little bit harder than probably, I think, what you'd see on the assignment. X cubed times. Okay. Something like that.
Yeah, that was one of them.
Okay, so there's something like that, yeah. Okay, so what about this? So let's have a look at this now. If we want to, before we jump into the derivative, it's always a good idea you gotta ask yourself, what's the domain, right? Okay, so is this domain potentially restricted?
Yeah.
It is, right, it is. And it is because of the x cubed is fine, but it's this square root part that could cause some issues, right? So let's kind of just focus for a second on just the domain. Okay, so a good way to think about this, and it's a couple of years ago, we probably talked about this a little bit in Algebra 2, is to think in terms of red flags. Where's the red flag? Yeah, under the square root, whatever's under the square root. So whatever's in the red bubble, what has to be true of whatever's in the red bubble in order for that square root to not blow up? Greater than or equal to 0, right? It has to be non-negative, right? So we're just thinking, does that make sense? Yeah. So we're just thinking whatever's in the red bubble. Ignore what's in it for a second. Whatever's in the red bubble, though, has to be greater than or equal to 0. So in other words, the argument of the radical has to be non-negative. Okay, well, what's inside the bubble? Now, if we actually look and see what's in there, well, it's the expression x plus 1. So all we have to do then is just solve this inequality for x to find the domain, right? So what do? Yeah, just subtract 1 from both sides, and so we get the domain. X has to be greater than or equal to -1, right? So then going back here, greater than, or if we use interval notation, what's that look like? Greater than or equal to -1. So I get a bracket, -1. Yeah, like that. That's supposed to be an infinity. Right? So there's my domain. Okay, now we can do calculus. So what is that radical? It's really a what power? 1/2. Okay, so our first derivative then is going to be what rule? Product rule. Okay, I'm going to do this one out of order so I can keep the bigger power of the radical in the first term. And you'll see why. I mean, can anybody think of a reason why I might want to do that? Yeah, when we get the derivative, in hindsight, tell me why I probably did that. Okay. So we get x plus 1 to the 1/2 times the derivative of the first, which is
3x².
okay, plus the derivative of the first, which is what? Oh no, sorry, the first, which is x cubed, times the derivative of the second. What's that going to be? 1/2 times and to the -1/2 times 1. Okay, so just that, right? Okay? Okay?
Will you go back for?
Sure. To the other page?
Oh, wait, no,
Okay. So how many different kinds of bases do we see there?
does that mean?
So so bases are, when we look at a power, we have a base and an exponent, right? So the bases are the things that are being taken to powers. How many different kinds of bases do we have there? Two. What's one base? X plus 1. Okay, so we can factor out the least common power of our like bases when we're factoring out common factors, right? So what power of x plus 1s do we get to bring out front? No, negative 1/2, right? What was our rule? Hunter told us our rule. We're going to take out the smallest exponent associated with each base, right? What's less, negative 1/2 or positive 1/2? Negative 1/2. Okay, so we're going to factor out an x plus 1 to the negative 1/2, right? And then what's the other base? Okay, an x squared. Good, an x squared. And so we can also pull out what power, so an x squared. 2 is the power of x. Yeah, there we go. So we get out an x squared, leaving us with some stuff. Okay, here's something else, though, that I would encourage you to do. I've got a fraction here, and I'd rather not deal with the fraction. I'd rather get rid of that fraction.
Let's do it.
So whatever fraction I have, if I can factor that away, that's the same thing as dividing both sides by that, right? So if I pull out a 1/2, which let's do, what's that going to do to, it's going to go away from this side, what's it going to do to this side? It's going to multiply by 2, right? Because really what I had here was an invisible 2/2. And I factored out a 1/2, leaving me with just the numerator, which is a 2, right? Factoring is dividing. It's a process of division. And so I'm just dividing away whatever I'm factoring out. Dividing by a 1/2 is the same as multiplying by 2, right? So what am I left with then? So we'll call this from the orange term, what are we left with? Okay, so we took out the x squared completely. Now, what's going to be the power of the base x plus 1? 1. It looks complicated, but I've really just got x plus 1 to the 1/2 minus 1/2, right? Everybody see that?
Yeah.
I divided away an x plus 1 to the minus 1/2. So I'm left with my 2
Well, times 3, right?
times x plus 1 times 3. Yeah, well, of course we can. Yeah, I just wanted to separate them so you could see kind of where they come from. Now, is it surprising that this is to the 1 power? No, not at all, because that's what happened in our previous example, right? We always got factor disappearing from one term and to the power of 1 in the other term, right? Because by the product rule, we're always subtracting 1 from the exponent. So the exponents are always going to differ by 1, right? Okay. How about,
We're using 3.
Plus x.
so the 3 comes from here. Oops, wrong color.
Oh, that turned into a 6. Oh.
Yeah, 'cause they multiply
It did.
2 and
Right, and then there's the 2 because we factored out a 1/2,
Never mind.
right?
And so did we take out a 1/2 from the other side?
Yeah, okay, we haven't gotten to that side yet. Let's do that side now. So we took out a 1/2, so that's gone,
Okay.
right? We took out an x squared, so that leaves us with a power of 1 of that base. And the other base has to be gone completely.
So
Okay.
plus x.
So we just got
Plus
Plus
x.
x, yeah. Is all we get from that second, from the green term, right? Okay, everybody see that? So now let's clean this up. So this gives us x squared over 2 times x plus 1 to the minus 1/2 times 6x plus x is 7x plus 6, right?
What's 7x plus
Did I do it wrong?
No, you're right.
And probably it wouldn't be a bad idea to write this, being as I have a negative exponent. For the purposes of finding critical numbers, it's probably not a bad idea to write this as a fraction. right? So I could write this as, on the top, I'm gonna get x squared times 7x plus 6, and on the bottom I get a 2 times the square root of x plus 1, right?
But wouldn't that make it harder to find the zero? Oh, because then,
Right, because now I know the zeros are gonna be where the top is 0, and the undefined places are where the bottom is 0, okay? But, where is the bottom undefined? So it's undefined only in places that aren't in our domain, except -1, right? So -1, I guess, technically becomes a critical number, although, think about this now, a critical number at an endpoint, does that really make a lot of sense?
yeah.
Not really, right? It wouldn't matter if we treated it like one, it's not gonna hurt anything, but it's not necessarily necessary, right? Okay, so we're about done, aren't we, of course? 1 minute. Okay, so here's where I'll leave this off for today. If we were not asking for inflection points, would you want to do a second derivative on this?
No.
Heck no. Why would you? We would just fall back on the first derivative test, right? See what I'm saying? Okay.